Hello, and welcome to episode 5 of our nuclear physics series for grade 12 physics. Today we're going to be taking a look at half-life and how that affects our understanding of nuclear reactions. In the past, we've looked at nuclear reaction types as well as how much energy is released by them. With our nuclear reactions, however, once that reaction takes place, we have a different nucleus, so that reaction cannot take place again. And like in chemistry, there is a specific rate at which these nuclear reactions can happen. And for decay reactions, that rate is determined by the amount of material and the half-life of the material. Logically, the more material you have, the more reactions will take place. But the half-life also determines how fast this occurs. Now, the half-life of a material is determined by the stability of the nucleus. Some nuclei are very stable, and so they will last a very long time before decaying. Some nuclei are very unstable and will last only milliseconds or microseconds before decaying, so you will have many more of them undergoing decay at any point. Now, with half-life, we have a fairly straightforward formula which will look really familiar to you if you've taken grade 12 pre-cal math. So here is our formula for half-life. With this, I have my activity at any given point in time is given by the original activity. So A naught here is my original activity. And that is times 1/2 to the power of T over T half. So T is the elapsed time, and T half is my half-life. So this is the original activity times 1/2 to the power of the elapsed time divided by T half. Please note when you're using this formula to do your BEDMAS and your order of operations correctly, you'll need to do this division before you take 1/2 to the power of whatever that is. And this here is my activity after activity after the elapsed time has passed. Now, the idea with half-life is fairly straightforward. When I start off, so let's start off with a nice easy number. Let's start off with 64 atoms. Almost wrote that correctly. 64 atoms of uranium-238. Now, uranium-238 undergoes alpha decay. So with our alpha decay here, this uranium-238 has a fairly long half-life. After one half-life for our uranium-238 here, we will be left with only 32 of these uranium. So this number is going to be cut in half. If you're curious, the half-life of uranium-238 is 4.47 billion years. So after 4.47 billion years, we will have 32 atoms remaining. So this is after one half-life. What this means is that half of these atoms will have decayed. Half of them still remain. After another half-life, so we cut it in half. Again, we cut it in half, so then I would have 16 remaining. And then I would cut that in half, and I would have 8 remaining. So if this takes 4 billion years, that would be 4 billion years, 8, and then this would be another 4, so 12 billion years, which is a long time to track uranium-238 atoms for. I probably should have chosen an example with a shorter half-life. So here's the formula. This here explains, and we can use that to calculate how many atoms are remaining. This will work for any period of time. So let's take a look at an example here. Again, this example will be in the class notebook. I will have them in there if you want to work through them at the same time. I will also have the solved example in there as well once I scan them. So in this case, we have radon-232 has a half-life of 3.8 days. So reading through this, my half-life, or my T-half, is 3.8 days. A sample has an activity, so that's my A0, my original activity, which would be 1.5 times 10 to the 10th becquerels. And I have an elapsed time of 2 days. Okay, fairly straightforward here. I'm going to plug this into the formula that I already know. So my formula is A equals A0 times a half to the power of T over T half. That means that my new activity is 1.5 times 10 to the 10th becquerel to 1/2 to the power of 2 divided by 3.8. And make sure you do this first. Make sure that you're following BEDMAS here. Do that before you do the exponentiation. So working through that, what I end up with is my new activity is 1.04 times 10 to the 10th becquerels. I'm not writing all the decimal places here. This is enough decimal places for half-life because we're not looking at something that requires as much precision as our mass or energy calculations do. So here are a couple of things you need to know. When I'm looking at this, a becquerel, 1 becquerel is equal to 1 decay per second. So this here means that there are 1.5 times 10 to the 10th, or 15 billion decays every second. That seems like quite a lot, but that is one way to measure radioactivity. 1 decay per second is 1 becquerel. This means that after 2 days, the activity that I can measure has gone down to 1.04 times 10 to the 10th becquerels. There are a lot of other measures of radiation, and those different measures measure different things, such as activity or such as how much radiation is absorbed by the body and how much damage it will cause. There's REMs, there's Röntgens, there's a whole bunch of different measures of radiation. We are looking at becquerels, which is decays per second here. Okay, now when I'm looking at my nuclear physics here, my half-life calculations, a common example and a common way to use half-life is to work backwards. So when I'm looking at half-life, if I'm going to be solving for my time here, my elapsed time, I need to do a little bit more advanced math in order to figure this out. So to work through the next example problem here, we're going to take a look at something called radiocarbon dating. So in this case, carbon-14 has a half-life of 5,730 years. Okay, right away, let's start writing this down. T half is 5730. That's years. Great. Now with carbon-14, all living organisms have a small amount of carbon-14 in them. This is important because cosmic radiation interacts with carbon dioxide in the atmosphere and changes some carbon-12 into carbon-14 at a very predictable rate. And that rate of decay versus change means that if I measure a gram of carbon in a living organism, I end up with 0.23 becquerels of radiation from the decay of carbon-14. That means from me or from the cookie that you're eating, the carrot that you're eating, there's 0.23 becquerels per gram of carbon activity that is measurable from there. And that's a really, really consistent number that we find everywhere around the world. Knowing that, if we know that living organisms start with that much activity per gram of carbon, we can use that to estimate how long it was since something died. Because that cosmic radiation interacts with carbon dioxide in the atmosphere, plants take that carbon dioxide. When we eat the plants, then that carbon becomes part of our bodies and then is measurable. Once we die, or once something dies, it stops taking in that carbon from the atmosphere or from other organisms, and it's that balance of carbon-14 to carbon-12 changes. So here's the idea. It decreases after death as carbon-14 decays. So if I say, let's find a tree fossil, say we have a fossil of a tree or some sort of tree that has a measurable carbon-14 activity of 0.163 BQ, that means my current activity is 0.163 becquerels. My original activity was 0.23 becquerels. And I'm trying to solve for T here, which is a little different. Plugging this into my formula, again, I'm going to go back to the same formula. My activity is my original activity times a half to the power of T over T half. Substituting in 0.163 equals 0.23 times a half to the power of T over 5730. So there's my calculation. Now, what I need to find a way to solve for T here. Unfortunately, T is in the exponent here, and solving for something in the exponent is not something that my normal algebra can do. So we need to go talk to our pre-cal math teacher and say, hey, how can I solve this? So we're going to use our log laws. Hooray for math. Here's a way that it's useful in another course, another physics thing, because we're solving for something in the exponent. So to work through this, I'm going to start off by just taking 0.163 divided by 0.23 equals 1/2 to the power of T over 5730. Now, I'm not going to do this division yet because I don't want to deal with those decimal places. My next thing is I can take the log of both sides here. So I can say log 0.163 over 0.23 equals log 1/2 the power of T over 5730. Like that. What I can do next is, using the properties of logs from my log laws, this here, I can move down in front here. So I can say log of 0.163 over 0.23 equals T over 5730 times log of 1/2. And now all I have to do is solve for T, because that's now basic algebra. So I can say 5730 times log 0.163 over 0.23 divided by log of 1/2 equals T, and I'm running out of space. I have solved for my time here, and what I end up with is 2,846.45 years. In this case, this fossil tree, died or stopped ingesting carbon from the atmosphere 2,846 years ago, which seems like a long time, but isn't actually that long. So for this, to solve a Half-Life problem for either time or half-life, if you're trying to determine either one of those two, then you need to use your log laws in order to solve that. Hooray for math. Thanks for watching. I hope you have a wonderful day. I'll see you next episode.